Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. I'm releasing a sample free response question from each of the 4 exams each week to help students prepare for the exam to, show what the free response questions are like and how the exam will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has access to the released questions to use in their own preparation, so this video series is primarily intended to assist those students. AP Central lists the following types of questions that students can expect to see on the AP Physics C Electricity and Magnetism exam. 1 will be on experimental design or have a lab-based component, and the 3 questions on the whole will assess all 7 of the science practices listed here. Today we'll be looking at the C Electricity and Magnetism exam from 2018, question number 3, which covered Ampere's law, magnetic force, and induction. The figures below represent different views of 2 long, straight, horizontal wires, 1 and 2, carrying currents I1 equals I and I2 equals 2I, respectively, in the directions shown. The wires are held in place. In figure 1, the current in wire 1 is directed out of the page, and wire 1 is a distance d above wire 2. Point P is a horizontal distance d from wire 1, and a distance d directly above wire 2. Express your answers to parts A and B in terms of I, D, and physical constants as appropriate. A. Use Ampere's law to derive an expression for the magnitude of the magnetic field at point P due to wire 1. So let's start with Ampere's law, which of course says that the integral around a closed curve of B dot dl is equal to mu naught times I enclosed. So how much current is inside this closed curve? So for this wire, we're going to remember that we can simply take an Amperian loop that is the circumference of a circle around the wire, and its circumference will be 2 pi times d, where d is the radius in this case, because d was the distance between point P and the wire, and that will be equal to mu naught times I, the current in wire 1. So this magnetic field, we could even call it B1, is equal to mu naught I over 2 pi times d. So for scoring, we're going to have 1 point for attempting to use Ampere's law, to calculate the magnitude of the magnetic field at point P. And then our second point is going to be for a correct answer. Part B, derive an expression for the magnitude of the net magnetic field at point P. Well, to know how to add these 2 vectors, we need to know how they're oriented relative to each other. So let's use the right-hand rule. Wire 2 has a current shown as such. So I'm going to turn so that this looks more like what you would see as you do the right-hand rule. So with our thumb pointing this direction, our fingers are going to curl and show the direction of the magnetic field around the wire. And at point P, our fingers are pointing into the page. And now with wire 1, you would do for yourself, your thumb pointing toward yourself, like so. And again, our fingers are going to curl around to show the direction of the magnetic field. So with wire 1 pointing out of the page like this, its magnetic field points straight up. So now take this diagram, and we are going to rotate our view so that we can see point P close to us, wire 1 in the background, and wire 2 below. So we would see wire 2 pointing into the page if we were in that perspective. And wire 1 we would see flowing to our left if we're in this perspective. And then here's point P that we can see in front of wire 1. So using our right hand rule again, the magnetic field due to wire 1 is going to be, or wire 2 rather, is going to be pointing to the right. And the magnetic field due to wire 1 is pointing up. So our two magnetic fields are at right angles to each other. So now we know that we can add them in quadrature. Quadrature using Pythagorean Theorem. So let me grab my pen tool. So our magnetic field for wire 1 we just saw was mu naught I over 2 pi d. And twice the current is going to be flowing in wire 2. So it's going to have twice the magnetic field strength. So we're just going to leave it like that. We're not going to reduce it further so that we can more easily calculate the net force, because they will have common denominators this way, or a common denominator this way. So since they're at right angles, we can add them using Pythagorean Theorem. So we'll do mu naught I over 2 pi d, the whole quantity squared, plus 2 mu naught I over 2 pi d, the whole quantity squared, and we'll take the square root of all of that, and that is going to give us B net is equal to 5 times the quantity mu naught I over 2 pi d squared. So we are going to end up then with the square root of 5 times mu naught I over 2 pi d. Clean up that d just a little bit and make it a little bit easier to read. So now let's talk about scoring. Here we're going to have a point for indicating that B2 is equal to twice B1. And then we're going to get a point for indicating that the magnitude of B is the vector sum of B1 and B2. Part C, calculate the numerical value of the angle to the horizontal for the direction of the net magnetic field at point P. So remember that edge on perspective that we took so that we can see both B1 and B2. That's going to let me grab my pen tool so we can think about our net magnetic field. That's a little bit too steep an angle. Let me fix that. So we can think about our net magnetic field is going to be something like this. A hypotenuse, and then here's our angle theta. And so we can see really clearly that theta is going to be the inverse tangent of B1, which becomes the opposite side of this triangle, divided by B2, which is the adjacent side to the angle. So if we substitute in the things that we know for B1 and B2, we know B1 is mu naught I over 2 pi d. We know that B2 is 2 mu naught I over 2 pi d. And everything cancels out except for a factor of 1 on top and a factor of 2 on bottom. Right. And the inverse tangent of a half is going to be 26.6 degrees. So let's talk about scoring. We're going to get a point for relating the angle to the individual magnetic fields. And then our second point comes from substituting, and actually I should put that a little bit higher because it actually is for that next step where we substitute for B1 and B2 into the equation that we developed that relates B1 divided by B2 as the inverse tangent. Part D, wire 1 is now released. Which of the following best describes the initial motion of wire 1 due to the magnetic field of wire 2? Assume gravitational effects are negligible. Our choices are: wire 1 will not move, wire 1 will move upward as viewed in figure 1, wire 1 will move downward as viewed in figure 1, wire 1 will rotate clockwise as viewed in figure 2, or wire 1 will rotate clockwise as viewed in figure 2. So my pro tip on questions like this, oh, and justify your answer. My pro tip on questions like this is to justify your answer first and then come back and make your selection second, because you can't make a good and accurate selection of an answer until you've thought the problem through. And the justify your answer section is where you can write out your thoughts and get it on paper and do the thinking through that you need to do in order to make that good selection. So clearly, we don't have room to do that on this slide, so on to the next. So I have shown, again, figure 2, so that we can talk through what does the magnetic field do to wire 2 look like at the location of wire 1. So again, if you think about your right-hand rule with your thumb going in the, how you are doing this for yourself. For me, if I put my thumb in the direction of wire 2, my fingers curl like this, and it looks like, relative to me, the magnetic field is into the page, but to you it looks out of the page. So that my right hand is doing what yours will do. Thumb in the direction of wire 2, and then curling around. When we are in the diagram above wire 2, we have a magnetic field into the page. Below wire 2, we have a field out of the page. So we're going to have just a couple of markings into the page here, out of the page down here. All right, so now we are ready to think about this justification. So in figure 2, the top portion of wire 1 will be in a magnetic field into the page from wire 2, and thus will experience a force to the right. And again, that's from another one of our right-hand rules, that with our current downward for wire 1, curled magnetic field into the page, we're going to get a force. Again, what your right hand is doing is to the right on the diagram. And then in the bottom half, if we have our same current I1, but now we need to be able to curl our fingers in the direction to point out of the page relative to you, that puts our thumb to the right. And so, well, my right, but to the left on the diagram. So the bottom portion of wire 1 will be in a magnetic field out of the page from wire 2, and thus will experience a force to the left. Thus, the net force will be 0, but there will be a net clockwise torque, so the wire will rotate clockwise. So let's talk about scoring. We are going to get a point for stating that the magnetic forces on the wire cancel, so there's no translational motion. So hang on, there we go. So basically this statement right here that I'm about to highlight, so the net force will be 0, will earn you a point, but then stating that there is a net torque that causes a clockwise, well, that causes a rotation, will earn you another point. And let me grab my highlighter one more time because it's just a little bit easier to work with. So hold please. Highlighter, there we go. Net clockwise torque. I wanted this one yellow so that, there we go. Net clockwise torque, so the wire will rotate. That's going to earn you your second point. And now we can select that wire 1 will rotate clockwise as viewed in figure 2, and there's no extra point for for the correct selection. Sorry, I just realized that I'd written the wrong thing here, but I selected the right thing here. It happens sometimes. This is why it's good for me to check my work, huh? Wire 1 is now replaced by a conducting rectangular loop of length L, width W, and resistance R. The loop is placed a distance D from wire 2 as shown. The loop, wire, and distance D are all in the plane of the page. The long side of the loop is parallel to the wire. The current I2 for wire 2 is decreasing linearly as a function of time, according to the equation I2 equals 2 I naught times the quantity 1 minus KT, where K is a positive constant with units of per second. Part E. Of the following, select the integration that will give an expression for the flux phi as a function of time t. So we are going to need to remember, let me grab my pen tool. We're going to need to remember that our magnetic flux is equal to the integral of B dot dA. So, got a couple of things we have to think about. Namely that our magnetic field in general is going to be mu naught I over 2 pi r, where r is going to be the distance from our wire. But here's the thing, that distance isn't constant, right? So that's going to end up being the variable that we integrate over. Well, gosh, that lets us home in on either this one or this one, because those are the only two options that have the variable r to integrate over, and no, that's not a typo. Not a typo. So, you know, and then we have to remember, of course, that our current here is given by that function 2 times I naught times the quantity 1 minus kt, and then the area of our loop is going to be given by L times W, but this W is parallel to R, you know, that distance from the wire, so we don't have to account for it in the area, because we're going to actually account for it when we are integrating over R. So that gives us the third option down, that our flux will be the integral from R equals D to R equals D plus W of mu naught times 2I naught times the quantity 1 minus kt all over 2 pi r times L dr. And this one, easy scoring, you get 1 point for selecting this one. Part F. Given that the flux through the rectangular loop as a function of the time t is given by the equation phi equals mu naught I naught L times the quantity 1 minus kt all over pi times the natural log of d plus w divided by d, derive an expression for the magnitude of the current, if any, induced in the loop. Express your answers in terms of I naught d little r, capital R, w, k, L, and physical constants as appropriate. Well, to get current, we're going to need the EMF. So we can remember, and let me grab my pen tool. So we need to remember that the EMF is going to be, we just need a magnitude. So the magnitude of the derivative with respect to time of the magnetic flux. And so we have a bunch of constants here. Mu naught, I naught, L over pi, natural log of d plus w divided by d will also be a constant if we had a value for that. And then that will be multiplied by the absolute value of d dt of 1 minus kt. So that turns out not to be that awful, actually, right? We just have a bunch of constants times an actually really simple integral. So this final term of d dt of 1 minus kt works out to be minus k. So we're going to have minus k times all of this stuff out front, but of course we wanted the, I really should be careful with that. We want the absolute value of minus k. Oops, hang on. We want the absolute value of minus k. So the negative goes away, is kind of the whole great big point of that, and we are left with an expression for the EMF that is mu naught I naught k times L divided by pi times the natural log of d plus w divided by d. Now we can get current, because of course the current is going to be equal to the EMF divided by the resistance. So we're going to take that whole great big expression for our EMF, and we're going to multiply it by 1 over r. And really, we could stop there, but if you want to sort of like simplify one more step and make it look that much prettier, you could have mu naught I naught k times L over pi times capital R times the natural log of d plus w divided by d. So let's talk scoring. We have a point for attempting to take the time derivative of the flux to calculate the EMF. And we have a point for dividing the EMF by R, resistance, to get current. Well, to calculate current. And then our final point is going to be for the correct answer. What is the direction of the current, if any, induced in the loop as seen in figure 3? Clockwise, counterclockwise, undefined because there's no current induced in the loop. Justify your answer. So once again, we'll justify first. Because the current in the wire is decreasing, the flux in the loop will decrease. According to Lenz's law, the induced current should create a magnetic field to oppose this decrease. Thus, the induced magnetic field must be into the page, and the current in the loop must be clockwise. And we'll select clockwise. So our scoring is going to be, there we go, plus a point for selecting clockwise, with an attempt at a relevant justification. We're going to get a point for indicating that the flux inside the loop will decrease. So once again, we're going to +1 this, and we're just going to highlight that. We're indicating this, that the flux in the loop will decrease. And then our final point is going to be for using Lenz's law right here in the middle to relate the decrease in flux to the clockwise current. Oops, I need to get back on highlighter tool. Hold, please. So Lenz's law. Oh my goodness, I'm just having a time of it right now. There we go. So we're going to use Lenz's law to relate the induced current, or to relate the decrease in flux to the clockwise current. So that's really going to be talking about all of this last few sentences here. So I hope you have found this demonstration of an APC electricity and magnetism free response question helpful. Notice that this is another kind that covers multiple topics in one question. So it's really rich and a fairly long question. If you have a problem you would like to see solved on my YouTube channel, you can send it to physicsproblemrequests@gmail.com, but I won't be putting any of them up until after I'm done with my AP Physics series. If you would like some email assistance, you can send your problem and the work you've done on it so far to freephysicshelpline@gmail.com with a limit of 10 questions per academic year. If you'd like to know more about my online physics tutoring services, you can reach me at brandyhevlinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. Just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics C Electricity and Magnetism exam, and those materials include the released free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scores for that year were looking for and how they decided to award points. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.